Okay, you guys, I recorded all these notes right here for 12.1 yesterday, but apparently my sound wasn't working. So we're just going to watch the same video again here right now, and I'm just going to kind of talk over it. So hopefully this is going to work. All right, so in 12.1, we're beginning a chapter, a tough chapter on circles right now, and we're going to begin with what I'm calling section 0 here, just on vocabulary. Now, we've already done a lot of this from section 10.6, so we're going to go quickly through the vocab here, and this should be just a refresher, hopefully, of some words and terms that you guys learned a while ago. So the first one we're going to talk about here is that a circle is simply a set of points that are all equidistant from a common point. So if we were going to draw a circle, we'd start with that one common point there, which we would call the center, and then basically draw a whole bunch of little dots that are all the same distance away from that circle. And if we drew a whole bunch of them, it wouldn't really look like a bunch of disjointed dots anymore. It would basically look like one big smooth circle like we're used to seeing. So there you go. That's our definition there of a circle consisting of an infinite number of points that I'm drawing here now that are all the same distance away from that center. Okay, the second term we're going to talk about here is a chord. And a chord is a line segment with both of its endpoints located on that circle. So let's go back to the diagram here, and if we were simply going to locate, they can either be existing or make new ones, but if we could locate 2 points located on that circle and then connect them, that's what we call a chord. A little bit different from a musical chord. Third one, diameter, and that's going to be a chord that passes through the center of a circle. So just like a chord, both of its endpoints are going to be on the circle, but a diameter has to pass right through the center there. So a diameter is your longest chord that you could possibly draw, and that is one of what all your diameters could look like. Okay, fourth term we had in this list, let's scroll down here just a bit, and D, we have a radius, which is a segment drawn from the center of your circle to any point located on that circle. So, back to the diagram we were working on here. Nope, that's not it. Here we go. If we wanted to draw a radius, we start at the center of our circle and simply draw a line segment going to any point on the circle itself. Okay, and that is what a radius looks like. Okay, those 4 terms there you guys probably knew before we even started talking about them in Chapter 10 this year. Those are middle school terms. But now E and F, these are new terms that I don't think you guys knew beforehand. A tangent is a line that intersects a circle at exactly one point. It kind of glances off the outside of the circle but doesn't really pass through it at all. So trying to draw a tangent can be a little bit tricky, but you want to think about like a ball resting on a table, and I did underline the word line right there. Unlike chord, diameter, and radius, which are all segments, a tangent is a line, which means it goes on forever. So what we'd probably do to draw a tangent would be to start with an external point, something outside the circle, and try to draw a line that just glances off the side of that circle one time with one point of intersection, what we call a point of tangency right there, and just glancing through it. So that is a good example of what we call a tangent line, everybody. And it's difficult to draw. You got to get it just right. This line that I just drew right here doesn't cross the circle at all. So that one is not a tangent line. And the other thing we're going to draw in just a second, there's a third possibility now, and the word for that is a secant. And a secant is a line that intersects a circle at exactly 2 points. So whereas a tangent only crosses it once, with a secant you don't need to be quite as careful. So a secant just shoots through a circle with 2 points of intersection. So arrows at the end indicate a line and 2 points of intersection. That tells us then that we are dealing with a secant line there. And in your book, there's a lot going on with theorems and lengths of secant lines. That comes at the end of the chapter, and we usually tend to skip those at this level, guys. So that these 2 words right here, though, are tangent line, really, that's the important thing we're going to be talking about today. So first thing we're going to do is Theorem 12.1. All right, and this theorem says the following, everybody. If a line is tangent to a circle, then the line is perpendicular to the radius drawn to the point of tangency. So as we go back to how to draw out a theorem, the if, the hypothesis of that theorem, is where we normally make our diagram. So one of the assumptions, or some of the assumptions we're allowed to make in a figure here, is that a point that appears to be in the middle of a circle is in fact the center. And a second thing is that a line outside the circle like this that appears to be tangent to the circle is tangent. So those are assumptions that we are allowed to make. And that point that I just drew a dot at right there, that is going to be our point of tangency, which is a phrase that I used a little bit earlier. It's the one spot where your tangent line crosses the circle itself. So we have ourselves a point of tangency. And now, back to the conclusion of this theorem, if that line that we drew is tangent to this circle, then that line is perpendicular to the radius drawn to the point of tangency. So we're going to draw the one and only radius that goes from the center of this circle to that particular point of tangency. So let me draw that in red. And here is the one radius now going from the center to the point of tangency. And this theorem tells us that that radius right there has to be perpendicular to that tangent line. So we know that we have a right angle formed if we draw a radius to our point of tangency. Okay. We're going to switch back to blue here, and what do we got? Oh yeah, if we don't have a tangent line, if we don't have a right angle there, you can see there's actually a second point of intersection, which means that second line I drew isn't a tangent, but it's actually a secant line. So that's kind of a quick explanation of theorem 12.1. All right, let's see a couple of examples at work here that illustrate what's going on with this theorem. All right, so we're going to solve for x in this problem. And again, it's worthwhile to talk about assumptions. We're allowed to assume that this round shape over here is in fact a circle. We're allowed to assume that P is the center of that circle. So there's our circle. We know we have a center, and we know, or we're allowed to assume, that this line down on the bottom of the figure that looks like it's tangent to the circle is in fact tangent. And that tells us, based on the theorem that we just learned, that if we have a radius drawn, I'm sorry, I'm still talking about the tangent line right there. So this theorem that we just learned tells us that if we have a radius drawn from P perpendicular to the tangent there, that we're going to form a right angle. So we've got, let's see, that piece right there, it's going to have 2 points of intersection. So that thing I just highlighted in green would not be a tangent, but the yellow line is. Okay, so back to it, I think. All right, so theorem 12.1 tells us that if you have a tangent line and you draw a radius to that point of tangency, we know that we have a right angle that's formed. Any day now. All right. So as we look at this figure, we have ourselves a right angle here that's going to be formed between the radius and the tangent. All right, at that point of tangency right there. So here comes our right angle. And now what's important to realize is that we have ourselves a right triangle inside of this figure, made up of the radius and then that tangent segment on the bottom right, and then this little piece going from the outside point back to the center. So kind of shading in green right there, there's our right triangle. And let's see what's going on. We're trying to find x, which is the length of one of the legs, but there's a little bit more information that we know here that might not be clear at first glance. We could see here that this entire hypotenuse of that triangle has a length of 25. But the part of the hypotenuse that's just outside of the figure right there only has a length of 18. So if we were to subtract the 25 minus the 18 that's outside, that tells us that the little piece of the hypotenuse that's inside the triangle has to have a measure of 7. And what's significant about that is that that 7 is the distance from the center of the circle to a point on the circle. That's the definition of the word radius. And all radii within a circle have to be congruent. So if that little piece is 7, that tells us that the red radius that we have coming straight down from point P has to have a length of 7 as well. And now, looking back at the green triangle that we shaded, I'm just going to redraw this down here to clean up the diagram a little bit. Here's our right angle. We know that we have a leg on the left of 7 and a hypotenuse of 25, and we're trying to come up with the length of the other leg, which is x. So we could definitely do the Pythagorean theorem here in order to figure out the length of that other leg, or if you were good with your Pythagorean triples, you might know the answer already, but most of us like to do it this way. X squared plus 7 squared is equal to 25 squared. Cleaning things up, that's going to be an x squared plus 49 is equal to 625. We'll subtract that 49 from both sides and get x squared equals, I believe, 576. And then take the square root of both the left and the right, and as dumb luck would have it, 576 is a perfect square, and x is 24. Now, as I said a moment ago, if you really knew what was up, this is actually one of your Pythagorean triples, everybody, 7, 24, 25. So as soon as you saw the 7 and the 25, you might have known that x was 24 right away, but most of us aren't real good with our triples, and this is a way that you can get around that. Okay, so that's example A using theorem 12.1. Let's take a look at another one, and this one, instead of dealing with side lengths, is actually dealing with angle measures. So this one's actually, I think, a lot easier. So, assumptions that we're allowed to make from the diagram. We can assume that we are dealing with a circle right here. We can assume that O is the center of that circle, and line segment DE certainly looks like, if we extended it, it would be tangent to that circle, only crossing it at one point right there. So, those are the things we're allowed to state about this diagram before we even get started. Now, back to theorem 12.1, it tells us that a radius drawn to a point of tangency here is always going to make a right angle with that tangent. We definitely have a radius from O to D, and D is a point of tangency, and that tells us then, everybody, that we are dealing with a right angle here in the corner, an angle ODE right there. So there's your right angle, and that means that the big triangle that we're looking at here has to be a right triangle. So we have that diameter, that hypotenuse, and that leg right there. And as we look at that right triangle, we know two of the three angle measures. We've got a 38-degree angle on the bottom and a 90-degree angle on the top left, so it should be pretty easy for us now to figure out the measure of that third angle. We know that the three angles in any triangle always have to add up to 180 degrees. So x plus 38 plus 90 is 180. Let's combine our like terms here to get an x plus 128 equals 180. Subtract that 128 from both sides, and we are going to get x is equal to 52 degrees then for the measure of that one right there. Okay, so like I said, I think that example was a lot easier than the one we just did in part A. Let's take a look at C now, everybody. This one's similar, maybe a little bit more complicated than the one we just did. Again, we're dealing with angle measures here, and in terms of the assumptions we're allowed to make in the diagram, yet again, we can assume that the blue figure is a circle, we can assume that O is the center, and this one actually looks like it has two tangent lines. LM looks like it's tangent to the circle, and NM looks like it's going to be tangent to it as well. So we actually have two tangents right here, and back to theorem 12.1, that means that we're really dealing with two right angles. Angle OLM has to be 90 degrees, and so does angle ONM. So both of those are 90. Now, there's a couple of different ways of doing this problem, but the easiest way is to recognize here that we're dealing with a quadrilateral. Now, in the last problem, we knew that in a triangle, the sum of our three angles had to be 180 degrees. In this figure, it would be really helpful to know that in any quadrilateral, the sum of your four interior angles always has to be 360 degrees in a quadrilateral. If you think about a square having four right angles, that's a quick way to remember that 360 right there. Okay, so since the sum of those four angles has to be 360, and we know the measures of three of them, it should be pretty easy to find x. We're going to add them all up. X plus the 117 in the middle, plus the two 90-degree angles that we have there, has to add up to a total of 360 degrees. Once more, we're going to combine like terms here on the left-hand side, and I think I'm going to cheat and use my calculator right there, but let's see, the 117 plus the 90 plus the other 90, looks like it's going to be, what, 307 degrees, if I'm not mistaken? Nope, I lied, 297, sorry about that. All right, so 297, x plus 297 equals 360. Subtract that 297, and we're going to get x has to be 63 for this diagram to work out. Okay, so three quick examples right there using theorem 12.1. Hopefully none of those were too bad. I think the first one was probably actually the hardest. All right, let's move on to theorem 12.2. And if the verbiage here in the diagram looked familiar, it's because theorem 12.2 is essentially just the converse of theorem 12.1. Theorem 12.1 said that if we have a tangent line, then we have a right angle. This one kind of says the opposite, or in the opposite order. If a line is perpendicular to a radius of a circle at its endpoint on the circle, then the line is tangent to the circle. So here was the original, here was 12.1. If you have a tangent line, then it's perpendicular. And theorem 12.2 says something different here. If you have a perpendicular line right there, a radius at your point of tangency, then we can conclude that that line must be tangent. So the diagram here, by the time we get done messing with it, is really going to look identical to the diagram that we had before. Here's our point of tangency, our radius is drawn, and this theorem now starts with the right angle. It says, okay, if you have a right angle, then you know this line outside here has to be tangent to the circle. I had one example prepared for you right here. I think we're actually going to skip this one. This really works pretty much the same way, and this one involves solving a quadratic equation, which is not something I'm going to ask you guys to do over e-learning. So I think the examples for that are going to look the same really, or those problems are going to look the same as they did for theorem 12.1. All right, theorem 12.3 is one that I like to call the ice cream cone theorem. You'll see why in just a second. It says that if two tangent segments missed that word there, are drawn from the same exterior point to the same circle, then the tangent segments are congruent. So we drew ourselves a circle. We have a point located outside of the circle, so that's what we call the same exterior point right here, and we're going to draw the two tangent segments that come from point A to the circle. Remember, a tangent only crosses a circle once. So I'm going to try to draw part of the line that comes out of point A that's tangent to that circle. So what I'm really drawing right here, guys, is a tangent ray. If I did extend it past that, it would be a tangent line, but that's really all I need. And here's the second tangent ray coming out of point A right here. So again, if we extended them, then sure, they'd be tangent lines, but we're only interested in what happens from point A moving back to the circle. So there's our two tangent rays, and that created 2 points of tangency. I'll call this one right here point B, and the one on the bottom right there I'll call point C. So if two tangent segments are drawn from the same exterior point to the same circle, then the tangent segments are congruent. Now, the tangent segments are just the portions of the tangent lines or tangent rays that come from point A to the point of tangency. So AB is one of our tangent segments, AC is the other. And this theorem tells us now, and I think if you guys hold this thing sideways, you can see why I call it an ice cream cone. This theorem tells us now, everybody, that those two tangent segments have to be congruent to each other. So line segment AB must be congruent to line segment AC, just like the two sides of an ice cream cone have to be the same length. Okay, so hopefully that's not too hard of a theorem to wrap your brain around a little bit. Wanted to do a couple of examples with you guys to show you what that thing looks like. So let's move on right here. Okay, so example 3A, we're going to try to find the perimeter of this triangle right here. So we've got triangle ABC, which kind of wraps around the circle right here that we had. All right. And let's take a look at what we know. We know the length of some of these tangent segments right here. Let me make that diagram a little bit easier and a little bit easier to simpler to see here, I hope. All right, and let's take a look at what's going on right here. So point A is a point that's located outside of the circle, and there's a tangent segment that goes from point A to point D, and we know that the length of that tangent segment is 10. The theorem we just learned says that if there's another tangent segment coming from the same exterior point there, guys, that'd be coming from point A here, that it would have to be congruent to that segment right there, okay? And so what that tells us, guys, is that line segment AF, that tangent segment, has to be congruent to segment AD. So AF is going to have a length of 10 as well. All right, let's switch colors right now. If we now focused on point B, we've got a tangent segment that goes from B back to D, and we know that that tangent has a length of 15. Any other tangent segment to the same circle from point B would have to be congruent. And there's another one right here. Line segment BE would have to have a length of 15 centimeters as well. Okay, we're getting there. And the last one, let's switch to red for this last one. From point C, we've got a tangent segment that goes from C to F. That has a length of 8 centimeters. And the tangent segment from C to E would have to have the same length. That would have to be 8 centimeters as well. So now, everybody, we know the length of all 6 of these tangent segments. And if we put them all together, that should give us the perimeter of that triangle. And there's a couple of ways to do it. If we put those 10s and those 15s and those 8s together, that should get us what we need. The 10 and the 10 is going to give us a 20. The 15 and the 15 is going to give us a sum of 30. And the 8 and the 8 is going to give us a 16. 20 and 30 is 50. 50 plus 16 is going to give us 66 centimeters now for the perimeter of triangle ABC. Another way to do it, and this is how I would probably do it, I doubt many of you would, but if we know everything is doubled, we could just add the 10, the 15, and the 8 together and then double that result. So if I took one each of all of those ones that we had there, and then doubled it at the end, it's basically using the distributive property, guys, or order of operations and cleaning up what's inside. So if I added just the 10 and the 15 and the 8 and then doubled the result at the end, let's see what that would get us. The 10 plus 15 would be 25. 25 plus 8 is going to give us 33. So there you go. Inside the parentheses, we're at 33. So 2 times 33, and sure enough, 2 times 33 once again gets us the same answer of 66 centimeters. So either way you want to go about it, both of those are going to work. Okay, and example B, last one we're going to do in this section, is now the same type of question, but they're giving it to you in a different order. They're telling you the perimeter of triangle PQR is 88. They want you to come up with the measurement here of QY, this guy right over here. All right, so to set this one up, let's take a look at what we know here, guys. Our perimeter, okay. Let's see what's going on. We've got another line segment that goes from Q to X as well. I'm going to call that piece N. I know everybody just wants to use X, but they already used an X within this problem. So if QY has a length of N, another tangent segment from the same exterior point to the same circle would have to be congruent to that. So if QY is N, we've got another segment, where am I going with this one right here, from Q to X that would have to be N as well. Here we go. But if PX is 15, PZ is going to be 15. If RZ is 17, then RY would have to be 17 as well. And here we go. If QY was N, then QX, right next to that, would have to be N as well. All based on the ice cream cone theorem here, guys, that says that 2 tangent segments from the same exterior point have to be congruent to each other. Okay, so I think we know everything we need to know to set up this problem. So here we go. The perimeter of this figure, we'll put a P right there, would equal, and let's just add up everything that we know, guys, and we'll make it easy. The 15 and the 15 is is 30. The 17 and 17 is 34. And then adding the N and the N together, there's 2 of them, so that's a 2N, and we know that the perimeter of this figure is 88 centimeters. So I'm going to set that perimeter equal to 88. And then from there, let's just solve a basic equation. Combining like terms, 30 and 34 is 64, plus 2n equals 88. We'll subtract that 64 from both sides and get 2n is equal to 24. And dividing by 2, n is going to equal 12. So that is the measure of QY. Okay, everybody, that's a wrap on this section right here. Let's give that 12-1 worksheet a shot and see how we do on it.